Justin Miller, Rockstar College Physics. We are back. So what we're going to do, we're going to continue looking at some constant acceleration. How are we going to do that? We're going to go ahead and do some problems. So let's do a couple problems here. First off, before we start the problems, I'm just going to write down the equations of motion that we've developed regarding constant acceleration in one dimension. We're going to stick with the x direction here. So we've got ourselves delta x is equal to 1/2 a sub x t squared plus v sub xi times t. Displacement is a function of time, and then we've got v sub x is equal to a sub x t plus vx initial. This is the velocity at some time t. So you could call it the final velocity, vx final, that's fine. I'll put a little f there, but it's just the velocity at whatever we choose to be the final time. Velocity is a function of time. Two fundamental time-dependent expressions for constant acceleration. Between these two equations here, there are 5 possible unknowns. 2 equations, you can solve for 2 unknowns. So, what do we have? If you know 3 of the 5 quantities, then you're able to go ahead and solve for them. So the method to do so may be lengthy or may require some other manipulations, but in principle, these 2 equations can be used to solve anything regarding constant acceleration, given that you know 3 quantities. So we've got 2 other expressions that come in handy that were developed ultimately through these equations, and we've got ourselves that vx final squared is equal to vx initial squared plus 2 a sub x delta x. Velocity is a function of displacement, and we've also got ourselves that delta x is equal to 1/2 times the quantity of vx final plus vx initial times time. So in all of these, we're assuming that we're starting at t equals 0. There's some initial velocity vx at t equals 0. It could be 0 or it could be non-zero, just depends on the expression. And then we've got all these other things going on here. Constant acceleration A, and so on. So here's the first problem. All right, so we've got ourselves an object that is subject to a constant acceleration of 5 meters per second. And then we're asked about some things. We're told that it's initially at rest, undergoes an acceleration of 5 meters per second squared, and we want to know how long does it take for it to travel the first 20 meters. And then we ask some other things about it too. So it's always a good idea in these types of problems with so many different quantities to keep track of to make tables. Make a nice little table of what you know, what you don't know, so you can see explicitly and reference explicitly what you've got to work with. So again, there's 5 quantities that we have to work with here. We've got a delta x, we've got a vx final, we've got a vx initial, we've got an a sub x, and we've got a t. And, well, given a particular problem, we've got to figure out which 3 of these we know to solve for whatever we're being asked for. So we are told specifically, again, that this object is subject to a constant acceleration of 5 meters per second squared in the positive x direction. So it starts from rest, it's going to move in the positive x direction. We'll just assume sign correlations for one dimension. Positive is positive, negative is negative x direction. So we've got that, and we're told that this object is initially at rest. So we've got that the initial velocity is equal to 0. So that's an important factor. And then what else are we told? Well, we're asked specifically what amount of time does it take the object to travel the first 20 meters. So we're looking for time, that's what we're asked about, and delta x, the displacement that the object undergoes, is going to be 20 meters. So this is what we've got. So how are we going to go ahead and figure out what the time is? Well, these are what we know, and these are the equations that we've got to work with. So we want to know time, given that we know the initial velocity, the displacement, and the acceleration. Look at this expression right here. We know delta x, we know a sub x, and we know vxi. The only thing that we don't know is t. We can isolate it, solve for it. So this would be the go-to for part A, and we just do that. So we go ahead and say that we've got, again, delta x is equal to 1/2 a sub x t squared plus vxi times t. That's our starting expression, and then we've got to go ahead and start manipulating things a little bit. Before we do that though, zeros are always nice because they can eliminate an entire term. We're told, again, initial velocity is 0. It's initially at rest. So this term right here goes to 0. We don't even need it. So that just gives us this little thing left, and all we got to do is isolate this t here. So we can multiply both sides by 2, divide by a sub x, take the square root, and we've got ourselves that t is equal to the square root of 2 delta x divided by a sub x. Then we've got t isolated. Now we can just go ahead and plug in the numbers that we have and solve for it. So at that, we've got ourselves that t is equal to the square root of 2 times 20 meters divided by 5 meters per second squared. And what do we got? We've got ourselves a root 8, 2 root 2, 2.828. 2.828. And what do we see? The meters are going to cancel out. We're left with, well, a second squared overall. Taking the square root of that, we're left with seconds, as we should. We've got the proper units here, seconds. And there we go. Could round that off to 3 significant figures. That's fine. Call it 2.83 seconds. But I'll just leave it like that for now. 2.82 seconds. Something that starts at rest, accelerates at a rate of 5 meters per second squared, will take 2.828 seconds to travel its first 20 meters. There we go. Doesn't matter what the object is. These are the constraints here. So we go on and we start asking some more questions like, hey, well, this object started at rest, it accelerated. How fast is it going after it moves 20 meters? So B, we're going to ask, what is the final velocity after moving 20 meters when it starts from rest and accelerates at a rate of 5 meters per second squared? So we've got still all the same constraints here. These two are constants. This depends on what we're talking about, and we're still asked about at the 20 meter mark. So we want to know what V final is. A couple different ways that we could get it at this point. Because we know how long it takes, we could utilize this expression and put t in there, 2.828 seconds. We know V initial, and we know a sub x. We could solve for Vx final. Or we could do it independent of what we just solved for and go to this expression here. Vx final squared is equal to Vx initial squared plus 2 a sub x delta x. And that's kind of already written in the form that we want. I'm going to use this one. It doesn't matter though. You could use either one, you're going to get the same answer. You better get the same answer or these expressions wouldn't be valid. So let me just use this one and we can write ourselves that Vx final is equal to, there is technically a plus or minus the square root of Vx initial squared plus 2 a sub x delta x. When you take the square root of something, there's a plus or minus, and we're going to have to pick which one it is. But in the end, we've got ourselves Vx final is equal to plus or minus the square root of, well, that's 0, plus 2 times 5 meters per second squared times 20 meters. And what do we get out of that? We've got the square root of 14.14. 14.14. What are we left with? Well, we've got meters times meters. This is meters squared divided by seconds squared. Take the square root of that, and we get meters per second, as we should. Meters per second. And we note that this object is moving in the positive x direction, starting from rest, so there's no reason that it should be negative. It's positive. So if we wanted to, we could put a little I hat here, but this is one-dimensional. It's already inferred that we're considering the x direction. Positive is positive, negative is negative, so generally, one-dimensional motion, we'll just leave it. There we go. We've got ourselves 14.14 meters per second. There is the velocity of this object in the x direction after moving 20 meters, or equivalently, after 2.828 seconds has gone by. All right, let us do something else here. Let us ask, hey, what is the average velocity? The average velocity of this object and it going from its initial position to the 20-meter mark. So now this is asking something different. So we'll put C over here and say that we want V sub x average. And again, we're considering 0 meters and 20 meters to be the initial position and the final position. Well, we know that by definition, average velocity is delta x divided by delta t. So that's all that we've got to compute here. We know that delta x is going to be 20 meters, and we figured out already how long it takes this object to move that 20 meters, 2.828 seconds. So we can go ahead and calculate that out, and we've got 20 divided by 2.828, and that gives me 7.072 meters per second. So there we go. We got ourselves the average velocity. So if we traveled at a constant rate of 7.072 meters per second for 2.828 seconds, we would move 20 meters. If we moved at a constant rate. Or when that's just the average value. On average, that's how fast we're moving. All right, there's something to notice here. Notice that this is 2 times this. The final velocity over that 20-meter distance is exactly 2 times the average velocity computed over that same distance. It's not a coincidence. That ends up happening because we have a linear change in velocity, a constant acceleration. So that's something that's well, always ends up to be the case. So nonetheless, not necessary to really point that out, but it's of a little interest. Let's do one more part with this. So we've got a part D here, and what I want to know, what we want to know, is at what time is the instantaneous velocity equal to this average? So this object is under constant acceleration of 5 meters per second squared. It goes from 0 meters per second to 14.14 meters per second over a 20-meter distance over a time of 2.82 seconds. Has to go through a transition, right? From 0 to 14.14. At some point in time in between 0 and 2.828 seconds, it will be going 7.072 meters per second. That's what we want to know. When does the instantaneous velocity equal this average value? When? So we've got something else going on, because it's not going to be at the 20-meter mark, and it's not going to be after 2.828 seconds, so we got to be a little bit more careful. So this is where we have to sort of redevelop what we know and what we don't. So again, we can write things out. Delta x, we've got a Vx final, we've got a Vx initial, we've got an A sub x, and we've got a t, kind of squeezing that stuff in there. But there's the 5 things that we generally are discussing. And this, we don't know what delta x is. We could guess. We don't want to guess. We want to know. We don't know. We know what the final velocity under consideration is. It has to be equal to this, 7.072 meters per second. This object is initially at rest, and its acceleration is 5 meters per second squared. What don't we know? We don't know the time, and we don't know the displacement of this object. We're really only asked about the time. At what time is the instantaneous equal to the average? So this is what we want to solve for here. We know those 3 things right there. We can look at our expressions and say which one's going to be most useful for us to figure out t. Well, something with delta x isn't going to really be helpful because we don't know what delta x is. So that leaves us with this one here. We know Vx final, we know Vx initial, we know A sub x. Hey, there's t right there. So with this particular part, we've got ourselves Vx final is equal to Axt plus Vx initial, and we can manipulate this, isolate t, we'll subtract vx initial from both sides, divide by a sub x, and write this out as t is equal to vx final minus vx initial divided by a sub x. Then we can go ahead and evaluate this, which gives us that t is equal to 7.072 meters per second minus 0 divided by 5 meters per second quantity squared, and we've got 0 divided by 5, 1.414, 1.414 seconds. So what I want to do is point something out here. The time at which the velocity, the actual velocity, is equal to the average over that 20-meter distance is exactly 1/2 the time interval over which that average was calculated. So we calculated the average over this time interval, 2.828 seconds, and then said, well, when is the instantaneous velocity equal to that average? And that happens to be at 1/2 the time interval over which the average was calculated, exactly 1/2 of this. That comes in to be very useful. That is something that is indicative of constant acceleration. And it can be utilized to, well, make some other characterizations and really figure out what sort of accelerations an object is subject to. We'll actually utilize this fact in one of the labs. And we'll use it to figure out a standardized acceleration. So, just to point that out, it's good stuff. There's a nice problem, and yeah, there's one. Let's do another one. Give me 1 second. All right, so we got another problem here. Make some room, and we'll take a nice look at that problem. Again, involving constant acceleration in a one dimension. Again, we'll stick with the x direction, and take a nice look. So, here's the problem. All right, so we've got ourselves an object that is traveling initially at 35 meters per second in the positive x direction. So that's its initial velocity. This object is then going to come to a stop over a distance of 80 meters, subject to a constant acceleration. So we want to know, first, what is that acceleration? So let's go ahead and draw out a little picture of something like this. Pictures are nice. Kind of give us an idea. We're going to start at the 0 meter mark, and we're going to stop at the 80 meter mark. We've got, let's say we've got some race car or something, I don't know. So there's some car there, 0 meter mark. Let's shift that over to be right there, where its nose is. And its initial velocity, Vx initial, is equal to 35 meters per second. And by the time it gets all the way over here, Vx final is going to be equal to 0 at that 80 meter mark. So we want to know, well, after it travels 20 meters, 20, 40, 60, 80, about right. After it travels 20 meters, no, excuse me, we're not concerned with that yet. That's part B. We're just concerned with what is the overall acceleration of this object. So I'll keep that up. Let's go ahead and write down some things. Sorry, getting a little ahead of myself here. So we've got ourselves a delta x, we've got a Vx final, a Vx initial, an a sub x, and a t, in no particular order, but so I'll write them down here. And say, what do we know, what do we not know? Well, if we know that this object is initially traveling at 35 meters per second. How fast is 35 meters per second? Well, you can roughly double it or times it by 2.2. What do you get? Like 77 miles an hour or so, a little bit more than that. But that gives us a rough idea of what we're talking about here. Some cars going 77 miles an hour, just going to stop over 80 meters. Is that even possible? Doesn't matter. We're just modeling this. At any rate, there's its initial velocity. Its final velocity is going to be 0 because it comes to a stop. Comes to a stop. So 0, and it does that over a distance of displacement of 80 meters. And we want to know what is the constant acceleration that this object is subject to. So what do? We go ahead and reference our equation of motion for constant acceleration. Well, I have a race, but that's okay. I'm going to write them up really quick again. We got ourselves that delta x is equal to 1/2 axt squared plus vxi times t. We've got vx final is equal to axt plus vx initial. Vx final squared is equal to Vx initial squared plus 2 Ax delta x, and delta x is equal to 1/2 the quantity Vx final plus Vx initial times t. So there we go, there's our equation of motion for constant acceleration that we've got going for us. We want to get acceleration, knowing displacement and the velocities. So what do we have here? Well, this one has time in it. We don't know anything about time. This one has time in it. We don't know anything about time. This one has time in it. We don't know anything about time. And it doesn't even have acceleration in it. What we want to know. This one has acceleration. Vx final, Vx initial, and delta x, the 3 other things that we do know. So that one's going to be pretty handy there. So let's take this expression and say Vx final squared is equal to Vx initial squared plus 2Ax delta x, and utilize this to isolate a sub x and then solve it. So how are we going to isolate a sub x? We can subtract Vx initial from both sides and divide by 2 delta x. That's it. So we can write ourselves that a sub x is equal to Vx final squared minus Vx initial squared divided by 2 delta x. So we isolated a sub x. Done a little algebra there. And then we can go ahead and plug in our values. We know this is 0. And then we have minus 35 meters per second quantity squared divided by 2 times delta x, which is 80 meters. So what do we get out of this? A sub x is equal to negative 7.656. Negative 7.656 meters per second squared. Comes out to be negative, right? Because it's a minus 35 meters per second squared there. What does the negative sign mean? Well, the negative sign means that the object is decreasing its speed because the object's moving in the positive x direction. If the acceleration is in the opposite direction, the object's slowing down, which makes sense because it's going from 35 meters per second to 0. If it was a positive acceleration and we said that that is the positive x direction, that would be increasing its speed. It couldn't come to a stop. So this minus sign is important. It's directional. If we wanted to, we could put a little I hat there so we know, hey, talking about the negative I hat direction, but it's already implied because this is a vector quantity and we're in one dimension, x direction. So there we go. There is the acceleration. Something you have to be careful of. It says an object slowing down, the acceleration better be in the opposite direction of the velocity vector. Bottom line. All right, so in one dimension. So we've got that. What else do we want to know? Now we start to ask some other questions. Like, how long does it take this object to travel the first 20 meters? So how long does it take to go from here to there? Well, that's a good question, right? Let's go ahead and solve that out. So now, let's set this one back. Let's say that we want to know Vx final at delta x is equal to 20 meters. Why do I want to write that down? Because we've got different constraints here. It's not the same ones as those. It's still moving at the 20 meter mark. So Vx final is not equal to 0, and we're not considering the 80 meter mark, we're considering the 20 meter mark. So we've got to, again, go ahead and write down what we know and what we don't pertaining to this particular aspect of the question, which is really important to wrap your head around. So we've got ourselves a delta x, we've got a Vx final, we've got a Vx initial, we've got an a sub x, and we've got a t. So we know that the displacement is going to be 20 meters, because that's what we're asked. We know that the initial velocity is 35 meters per second. That's a constant of the situation here. And we've got ourselves a sub x that we've just solved for being negative 7.656 meters per second squared. And, excuse me, it's part C. Time to get to. This is part B. We want the time that it takes to get delta x is equal to 20 meters. All right, so this is what we're asked for. Time. So let's go ahead and figure out that time, right? That should be pretty easy. We can go ahead and reference our expressions here, our equations of motion for constant acceleration. We know delta x, Vx initial, and a sub x, and we want to know what Vx final is. Look at this. We've got an a sub x, a delta x, a Vx initial. We know all those. And this is, I'm still doing Vx. Got that in my head. We want to figure out time, sorry. So how are we going to get time here? Well, look at this. We've got ourselves delta x, yes. We've got a sub x and Vx initial. And there's time in there. None of the other ones are going to allow us to do that because they all involve a Vx final that we do not know at this point in time. So how are we going to get it? Well, let's just go ahead and take a look at that top expression and go with delta x is equal to 1/2 ax t squared plus vxi times t. Say we want to isolate t. So this one's got to be a little bit more careful with, because the initial velocity is not equal to 0. This term does not go away. Neither does this term. We've got something that's quadratic in time, and we want to solve for the time. And, well, there's a quadratic term and a linear term. How are we going to isolate it? We can't just move things around and group the t's all together. It doesn't work out. You factor out one t, but you still got one t in there. Not going to do it for us. Furthermore, delta x is not equal to 20 meters, which, excuse me, it's not equal to 0. It's equal to a non-zero value, which complicates things a little bit. So how are you going to solve this? And the answer is quadratic formula, right? Quadratic formula is going to solve this out for us. So we could go ahead and utilize the quadratic formula and see what we've got going on for us. So got ourselves a quadratic formula. First off, we need the expression in standard notation for utilizing the quadratic formula. So we need something that says like at squared plus bt plus c is equal to 0, and then the quadratic formula itself is the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. And this is t equals that. There's two solutions, one for the plus, one for the minus, and there we go. So we've got to figure out what a, b, and c are according to this. So let us do this really quick. We'll first write it in standard formation or standard notation here like this. How are we going to do that? We'll just subtract delta x from both sides. And we could write this as 1/2 ax t squared plus bxi times t minus delta x is equal to 0. So now we can make the correlations with a, b, and c and these quantities here. So a is going to be equal to 1/2 a sub x. B is going to be equal to vx initial. And c is going to be equal to negative delta x. There we go. So that's what we've got going for us. So we could go ahead and quantify these because we know what a sub x is. A sub x is negative 7.656. So negative 7.656 divided by 2. We got negative 3.828. Negative 3.828. So there's our a value. B is just equal to Vx initial, which is 35. I'm just dropping units here. 35, and delta x is equal to 20, so negative delta x is a negative 20. So there we go. So what can we do with this? We can go ahead and stick it in the quadratic formula now, and this should be capital A, sorry, and figure out what the time is. So I know a lot of people don't like the quadratic formula. Sometimes you have to use it. Sometimes there's ways around it, which we'll get to with this. But nonetheless, it's good to have it programmed in your calculator, but this is a new calculator for me, and I don't have it programmed in here yet. So that's no good for me. One second, I got my other calculator over here. All right, found it. Here we go. So I've got it programmed in here. We can just as well stick it in the calculator, but there's a lot of room for error in that. So I'm just going to utilize this. 3.828. For A, B is 35, and C is negative 20. And I get 2 answers. So I get that T1 is going to be equal to 0.60875, 0.60875 seconds, and T2 is going to be equal to 9.3203, 9.3203. I'm keeping some extra figures here, that's okay. But we've got these 2 times, both positive and both real. So what does that mean? Shoot, which one's right? And which one's, well, why is there 2? So generally, you're going to get 2 answers. Sometimes one will be positive, one will be negative. Negative time means nothing for us. We're not doing any time reversal stuff. So if one of these had been negative, then we'd know definitively. We take the positive one, we're only interested in positive times, and that would be that. The fact that we get 2 positive answers is maybe a little perplexing, but we need to be able to make sense of things. That's what we want to do in this course, right? Make sense of stuff, not just make it about numbers. So we think about this. This object starts at the 0 meter mark and comes to a stop at the 80 meter mark under this acceleration. So it's going 77 miles per hour, approximately 35 meters per second initially, and starts slowing down. 20 meters isn't really that large of a distance, so it should stand to reason it's not going to take 9 seconds for it to just travel 20 meters when it's going 35 meters per second initially, even though it's slowing down. So you could kind of reason this out. It shouldn't be this. It should probably be this. This one would make a little bit more sense. You could check it out, but T1 is going to be actually the answer. But what is this T2? What does it really mean? Well, what it means is that it's another point in time that it could be at that 20 meter mark, that its displacement could be 20 meters from where it initially is, physically. So this is what we have. If this object's acceleration continues throughout time to be negative 7.656 meters per second squared, this object slows down at that rate, comes to a stop. But if this acceleration continues, well, that acceleration is changing its velocity into that direction. So now the object would start to speed up in the negative x direction. And at some point in time, it would be back at this 20 meter mark, having an overall displacement of 20 meters in the positive x direction, but traveling now in the negative x direction. So that's what this 9 seconds correlates with, 9.3 seconds. That's how long it would take an object that continues to undergo this acceleration to get back to the 20 meter mark for that second time. So both of the answers are technically correct, but we'd be more interested in the first time because kind of assume that this object comes to a stop and stays at a stop, but if it's not clearly stated, hey, you can go ahead and say either or both. We'll take this one. All right, so this is first time delta x is equal to 20 meters. And we'll say that that's our answer. All right, so that was fun, right? Yeah, of course it was. So what else do we want to know? Let's figure out some other things. How about what I was trying to force us to do, and we ask ourselves, how fast is it going when it reaches that 20 meter mark? What's the object's velocity at the 20 meter mark, that is? So v sub x final is equal to what? At delta x is equal to 20 meters. And we'll go ahead and put in this contingency first time. So we ask ourselves again, what do we know? What do we not know? And we've got ourselves delta x, vx final, vx initial, a sub x, and t. Well, we know that delta x has to be the 20 meters. We know that vx initial is 35 meters per second. We know the acceleration is negative 7.656 meters per second squared. We've just figured out the time it takes to get to this, 0.60875. I'm not going to write that down though. Let's see if we can just get what the final speed is based upon these three quantities here. So, can I erase the equation of motion for constant acceleration, but we could kind of look at those and note that we have an initial velocity, an acceleration, and a displacement, and we want to know what the final velocity is. There's no time in this, just knowing these three. So what could we do? Well, there is Vx final squared is equal to Vx initial squared plus 2 a sub x delta x as an expression. And well, we can utilize that. So let's just do that. So we can get ourselves that Vx final is then equal to plus or minus the square root of Vx initial squared plus 2 a sub x delta x, which then gives us, we would choose the positive because it's traveling in the positive x direction. So we can kind of drop that and say that this is going to be positive. Well, we've got quantity of 35 meters per second squared plus 2 times negative 7.656 meters per second squared times 20 meters. And we stick this in calculator, Mrs. Calculator for that matter, and what do we got here? Square root of 35 squared plus, no, let's just do minus 2 times 7.656 times the 20, and that looks good. We got ourselves 30.311. So this object will be traveling at a rate of 30.3 meters per second after it moves the first 20 meters. The rest of the distance, it goes from 30.3 down to 0. That's it. And that would kind of be that. So this was, getting this mixed up. This is a part C. Let's ask one. Oh, nope, let's not ask something else right yet. Let me illustrate something here. We were asked for the time first and then the velocity regarding this 20 meter mark. What would have happened if we were asked in the other way? Well, we could have solved for this, right? We didn't use time to get what this final velocity is. So 30.311 meters per second. Could we use this along with a couple other quantities to figure out the time? And the answer is yeah, of course we could. We have enough information where we could do something like, hey, Vx final is equal to axt plus Vx initial. And we can solve this for time. Time is equal to Vx final minus Vx initial divided by a sub x, which we could say is 30.311 meters per second minus 35 meters per second divided by negative 7.656 meters per second squared. And let's go ahead and put that on the calculator and see what happens with this, right? Trying to get used to the new one here. So we've got ourselves a quantity of 30.311 minus 35 divided by negative 7.656. And 7.656, 6.1246. 6.1246. Something in here wrong? Yes, I did. So the answer becomes 0.612. 0.61246 seconds. So, one thing here, bypass the quadratic formula. Bypassed it, didn't need it, we could solve for this to get the time. Even if we weren't asked for the final velocity, we still could just solve for it and then utilize it to get the time, so we don't have to use the quadratic formula. So there are ways around it sometimes, and this would be one of those times. But nonetheless, that's pretty easy instead of going through all this quadratic formula stuff. One thing to point out here, I made a little mistake, not in any of this, but this quantity and this quantity are not correct because I put in one of the values wrong because I'm not wearing my glasses. I would blame it on my glasses at this point. We were saying A, B, and C, 3.82848, negative 3.828, and somehow I put negative 3.525. Ooh, that's no good. So I got the wrong answers here. So let me erase this. They're close, but they're not what they should be. And let me do this again. Program. So A, negative 3.83828. All right, that's right. And 35, and then negative 20. And, all right, so this is what we get. T1, 0.61245 seconds, and then T2 is 8.5307 seconds. It was close, 0.602, but it's really 0.61245 seconds, according to the quadratic formula. So what we can do is notice that, hey, this and this are basically the same. There's one significant figure difference, or one numeric digit difference between the two, and that has to do with this and this being sort of rounded values. Mostly I'll blame it on this one. It's okay though. The three significant figures, 0.612 seconds to get to that 20 meter mark. Without the quadratic formula, or with the quadratic formula, we're getting the relatively same answer. Ah, all right. Sorry about that. At least I caught it. At least I caught it. All right, one last question, and then that'll be that for this particular fantastic problem. And that last question is, this is part D. What is the object's velocity ten meters before it stops? X final 10 meters Well, we could go ahead and solve for that, right? Because we've got a delta x, we've got a Vx initial, we've got a Vx final, we've got an a sub x, and we've got a t. We don't know t. but we do know some of these other things. We know the initial velocity is 35 meters per second. We're asked specifically, what is the final velocity at specific position? Negative 7.656 meters per second squared is this. And then we ask ourselves, well, what else do we know? We've got to know one other thing, and that would happen to be delta x, right? 10 meters before it stops. So 10 meters before it stops is going to be about right there. 10 meters, 20 meters, here is the 60 meter mark. So what does this have to be? 70 meter mark. So after it undergoes a displacement of 70 meters, it'll be 10 meters before it stops. We want to know how fast is it going. So here we go, 70 meters. We'll utilize these three pieces of information to go ahead and solve for this. We don't know time. We could solve for it first if we wanted to, but we're not really asked about it. So what can we do? We can go to the Vx final squared is equal to the Vx initial squared plus 2ax delta x. And that just gives us Vx final is equal to, we'll drop the plus or minus because we're going that way, and we've got ourselves 35 meters per second, quantity squared plus 2 times negative 7.656 meters per second squared multiplied by 70 meters. We've got ourselves Vx final is equal to, should it be going fast, should it be going slow? It should be going relatively slow, right? 10 meters before it stops. It was initially going 35 meters per second. It's pretty close to stopping. So we should expect it to be pretty small relative to 35 meters per second. And we're just going to do this squared minus 2 times 7.646 times 70. And we get ourselves 12.376. Let's slow it down quite a bit. That last 10 meters, it goes from 12.376 meters per second down to 0. And that's it. The whole time being subject to this constant acceleration. So what's the point with all of this? Really the point is that given a specific parameterization of an object's motion and enough information, we can talk about anything. We can figure anything out regarding that object. Where it is at any point in time, how long it takes to get to some point, how fast it's going at some point in time, or some position in space. All of those things, what acceleration is necessary to produce a certain effect, all is within the equation of motion for constant acceleration for an object subject to constant acceleration. Pretty cool. Pretty cool. This is what we want to be able to do. Understand. So again, don't make this just math, just numbers. Try to have some physical connection with it. What's going on? What are we doing here? Don't just make this about solving things. Make it about understanding what you're doing. All right, that'll be that. We'll be moving on to some more material here next round. Have a good one.